Good evening. Today we look at electrophilic aromatic substitution reaction, and of the electrophilic aromatic substitution reactions, we'll tackle the following: being halogenation, okay, sulfonation, alkylation, acylation, and nitration. Yes. So the above listed reactions will be followed respectively from the first to the last, and beginning we'll start with halogenation. So let's look at a complete reaction of halogenation. So using benzene as a raw material, we are requested to halogenate or undergo a halogenation reaction using benzene as a starting material. So if we're faced with this question, we have to list the complete reaction as the first step. So the first step is we list the complete reaction. Before we undergo any mechanism, we list the complete reaction, which is a reactant benzene. Benzene is reacting with, since it's halogenation, we are adding a halogen. So we can use any halogen, preferably I'll use bromine, Br2. And then the catalyst for this reaction that will be used will be iron bromide. Iron bromide will be the Lewis acid I'll use in this reaction as a catalyst. And the product I'm to attain is bromobenzene. Bromobenzene as my product, and the catalyst iron bromide, which was unchanged throughout the reaction. Okay, so this is the full reaction of the halogenation of benzene. So let's look at the step-by-step mechanism of this reaction. Step one of this reaction is involving electrophile formation. So electrophile formation will use our Lewis base, which is iron bromide, and we'll react it with our reactant, which is bromine atom, which is Br2. Yes. So the reaction between iron bromide and bromine 2 will yield an electrophile and a conjugate base. So we have bromine in molecular level looking like this, a halogen, so it has 3 lone pairs. Let's pay particular attention to the lone pairs and the movement of the lone pairs. So each bromine in the bromine atom has got 3 lone pairs, and this bromine molecule will react with iron bromide, which is our Lewis acid. So the empty d orbital of the iron will abstract or get to a lone pair from one of the bromines. So from one of the bromines, a lone pair will be abstracted, which will form a catalytic complex. So the Br2 and the iron bromide will form what we're calling a catalytic complex, which involves a bromine and another positively charged bromine, which has lost its lone pair to iron, forming this compound, which is highly unstable. So our iron here has gained electrons, so the iron will be relatively negative, and the bromine has lost a lone pair of electrons, so it will be relatively positive. Let's pay attention to this catalytic complex, as this catalytic complex will yield us our electrophile and our conjugate base. So the bromine is a highly electronegative atom, which wouldn't exist in a positive form. So the nearest bond between it is the bond between bromine, the second bromine. So this bond has 2 electrons. What this positively charged bromine will do is it will attract the 2 electrons from the bond, to stabilize the positive charge because it can't exist in a positive state. So this abstraction will lead to breaking of this bond, and when this bond breaks, will result to having a bromine who has lost its single electron. So our bromine will exist in a positive charge. So we've created our electrophile, and then the rest of the molecule will form our conjugate base, that is Br, iron, bromide. And let's not forget our iron is still negatively charged. So this is our conjugate base, and then this is our electrophile. So this is the first step of the halogenation of benzene. Let's go to the second step. Okay, the second step involves aromatic attack, step 2, which is the aromatic attack. And in this step, we'll have our benzene ring. We'll have our benzene ring reacting with our electrophile, which we created in step 1, which is the bromine ion, the positively charged bromine ion. So this bromine ion will act as our electrophile in the step 2, which is the aromatic attack, and will abstract any of the pi bonds in the aromatic system. So any of the pi bonds in the aromatic system can abstract this really positively charged bromine atom. So there is an attraction between the pi bonds of the aromatic system and the positively charged bromine. So I'll use this pi bond system, and then these pi electrons will stabilize that bromine, and as a result, this bond will break. Okay, so if this bond breaks, then we have this as our resultant molecule. Okay, so this bond that existed here has been broken, and we have a new bond being formed, which bromine has formed here. And the broken bond was involved with this carbon. So this carbon has to now possess a positive charge because it has lost some electrons from the pi bond. So we'll notice that this carbon will have a positive charge right there, and then the rest of the double bonds are maintained. Yes, so this is the aromatic attack, and from this attacked intermediate, we are able to realize resonance structures based on the movement of the positive charge in the ring. So what will happen at this point is the nearest pi bond to the positive charge can resonate to stabilize the charge. So this pi bond right there will move to stabilize this positive charge, and as a result here we'll have a molecule resonate, and we call this phenomenon resonance. So this pi bond will shift towards the positive charge, forming a new pi bond here, and then the carbon that was involved in the previous pi bond will now possess a positive charge because it has lost some electrons from this bond. So this carbon here will possess a positive charge, and then this double bond maintains. Yes, so that's the second resonance structure. And as we can see, there is another adjacent double bond to this positive charge, which can as well stabilize to form our third resonance structure. Follow carefully as we form these structures. They will be necessary. So this leads us to our third resonance structure. So after this double bond stabilizes this charge, it breaks the bond that was between this carbon and this carbon. So this carbon gets a relatively positive charge. So the positive charge shifts from here to here. So we have our charge on this carbon right here, and then we have a newly formed double bond here, and our previously formed double bond here. Yes, so this positive charge only has the newly formed double bond as its adjacent pi bond, so it can no longer further resonate because it will form this structure again. So when we reach this level where the resonance is taking us back to a previous resonance structure, we end the resonance, and that's our resonance after we do the aromatic attack in step 2. So with these resonance structures in check, we draw up what we are calling our uranium ion from the resonance structures. So our uranium ion will be based on the movement of the positive charge. So the movement of the positive charge in the ring will guide us on how our uranium ion will flow. So the positive charge started from here and then moved to here. So the positive charge was flowing through till here. So the resonance will move from this positive charge and the positive charge there. This is our uranium ion. Uranium ion, if we're required to produce an uranium ion, that's how we can produce uranium ion based on the migration of the positive charge, the limits the positive charge had reached. So let's go to step 3, which is a restoration of aromaticity. Alright, step 3 consists of electrophilic aromatic restoration. So we want to restore the aromaticity of the newly reacted ring. So the first resonance we had in the previous step included bromine, which has been reacted with a benzene ring. So this was the product, this was how the intermediate looked, and we had a positive charge on this carbon which was involved in the pi bond that was broken. So this is our intermediate for the aromatic attack. So this is what we use in step 3 of the reaction. Okay, so we had created a conjugate base in step 1 of the reaction, and that's what we use as our reactant in the third step of the reaction. So this conjugate base, where iron had a negative charge, we'll have to restore aromaticity to this ring. Okay, so this bromine that's attached to this iron is having 3 lone pairs. This makes it stable, relatively stable. And what we notice is that our iron has a relatively negative charge. So this iron is an electropositive atom and it's attached to something more electronegative. So the electronegativity of the bromine will cause this iron to lose this relatively negative charge to this pi bond. And for this pi bond to break and give its 2 electrons to this stable bromine. So bromine already has 3 lone pairs, so that means it's stable, and we're giving it 2 more electrons. So that means this bromine atom will be relatively negative. So this negative bromine is what we use as our reactant to restore aromaticity to this ring. So on this bromine atom, remember on the hydrogen, on a benzene ring, each carbon has a hydrogen attached. So on this carbon, we have our hydrogen attached here. And what we notice is that the negative charge of the newly formed bromine atom will obstruct this hydrogen and form a bond with this hydrogen. Thus, this hydrogen will break its already existing bond with the ring structure. That means the 2 electrons used to form this bond will be used to stabilize this positive charge. And as a result of this reaction, we'll have hydrogen bromide being formed as a result of this union of the hydrogen and the bromine. And the resulting bromine atom now forms a pi bond system to stabilize the positive charge. So our resultant product, overall product, will be as shown. So there will be a newly formed pi bond here and already existing pi bonds here. So the hydrogen had been lost. We formed our hydrogen bromide as our sub-product, and our major product is the bromobenzene. So this is how you halogenate a benzene ring.